Okay, so number two. Number two is a really good one because it forces you for the first time in terms of a problem here to make your electrons lost match your electrons gained using a coefficient out in front. What I mean by that is you'll notice that when you write, first of all, how many people wrote your oxidation numbers? You always start with that because if you don't do that, you can't figure out which one gets oxidized. Remember, that's the number that increases, or which one gets reduced. That's the number that decreases. So for this one, I saw that magnesium went from 0 to +2. That tells me that is the loss of electrons, which is oxidation. I ended up writing Mg goes to Mg plus 2 electrons. Why did I put the electrons on the right? Because it is Leo. And if you remember, we have Leo, Ra, up, and right. So I put those on the right. Now for Ger, I go to my reduction, which is the species that goes down in oxidation number. I start with Fe plus 3. You may not immediately know that it takes 3 electrons, so just go Fe plus 3 plus blank yields Fe. Then you can see, okay, if I go from plus 3 down to 0, I've got to add 3 electrons. You do that right there. Now comes the problem. Electrons lost, 2. Electrons gained, 3. We do not have the conservation of charge. Excuse me. We've got to get those the same. So to do so, we've got to use the lowest common multiple between 2 and 3, which we know is 6. So what do we have to do to 2 to get it up to 6? Multiply the entire thing through by 3. So you get 3mg yields 3mg plus 2 plus 6 electrons. Then for the second one, we have to multiply the entire thing through by 2. 2Fe plus 3 plus 6 electrons yields 2Fe. Now our electrons lost equal our electrons gained, and we're ready to add the two together. When you do so, you get 3mg plus 2Fe plus 3 plus yields 3mg plus 2 plus 2Fe. They want to know what is the smallest whole number coefficient on mg, and so right there it is, 3. Did anyone do it correct with writing out the half reactions, doing the correct balancing, and so forth? Good. So you probably got the right answer? Because in that case, the side of the electrons didn't affect the coefficient. But okay, good job, Faith. Okay, number 3. What I'm going to do for a moment is have you try it right now the correct way on your own. I'm going to be doing it up here. You try it because it sounds like most people struggled with setting it up correctly. So let's try this one basically together. We've got calcium plus aluminum ion yields calcium ion plus aluminum. First thing I need to do is assign some oxidation numbers. So Madison, go down through those and whip them out.
0.
Yep.
3.
Yep.
2.
Yep.
0.
Good job. Okay, if it stands alone, it's 0. If it's an ion, we know it's equal to the charge. Now we're ready to do hookups.
I thought they equal 0.
This is an ion. So any ion, the charge is equal to the oxidation number for any ion.
But I thought the side had to equal 0.
No. The charge on the left and the charge on the right will eventually be the same, but that's only when it's balanced. Okay, this isn't balanced yet. We're getting there. Okay, I need some hookups. What do I hook up with calcium? Ca to Ca plus 2 and label it what? That is indeed Leo. Ra, up and right. And what do we then hook up? Aluminum ion to aluminum. And we label that our Ger, OA, down, left. Okay, I need someone to volunteer to write the oxidation half reaction. So we'll do our oxidation on the left. We'll do our reduction on the right. Who's got oxidation for us? Go ahead, Claudia. Yep. Very good. Ca yields Ca, I messed this up here, plus 2. And then how many electrons? Well, very good. Plus 2 electrons. Good job. Ca yields Ca plus 2 electrons. Does everyone see how you use your brackets to get that? You know that you go from Ca over to Ca plus 2, and she did this correctly by putting the electrons on the right because of it being an oxidation half reaction. Loss of electrons is oxidation. Next, can someone do our reduction?
Al plus 3
Al plus 3.
plus blank electrons. I haven't figured that out
Yep.
yet. Yield
Al.
Al.
Good job. And what would we put in there for electrons, Kaylee?
3.
Very good. Okay, this problem now is really similar to the one we just looked at. What do I need to do at this point? I can't add them yet. Sophia? I need to get electrons lost and electrons gained to be equal. Very good. So I'm going to multiply the left-hand side by what number? No.
3.
There you go. You see why? I got to get it to 6. Yep, and 2 times 3 is 6. And the right-hand side, I'm going to multiply by 2. So let's go ahead and whip those out. We get 3Ca yields 3Ca plus 2 plus 6 electrons. Over on the right, we have 2Al plus 3 plus 6 electrons yields 2Al. Very good. Okay, Caleb, at this point, what can I do with those two half reactions? Very good. I'm gonna stick one underneath the other before I do that. I do agree with you that we can get rid of the electrons because they are the same on either side of the arrow. So our electrons get canceled out. Now we add together what is on the left, so we get our 3Ca plus 2Al plus 3 yields 3Ca plus 2 plus 2 aluminum. Now, Kaylee, let's check our balanced equation to see if we've conserved mass and charge. We've got 3 calciums, 2 aluminums, 2 aluminums. Now we'll check charge. We've got a total of 2 times plus 3, which is plus 6. 3 times plus 2, which is plus 6. So we have plus 6 on the left, plus 6 on the right. We're golden. And the question there says when the equation is completely balanced, what is the coefficient of Ca? And the answer obviously is 3. Coefficient of Ca. Anyone get that one on their own? Sophia, Mitch, good job. And everything but
The
the
only thing I did, I missed the electrons go on, so I just had to
gotcha. So it sounds like you do that every time.
Well, yeah, but I did it. I don't do it like that. I do a lot with it.
Okay, number 4. Number 4, the first thing again you're going to do is assign your oxidation numbers. Fe is 0, Ag is plus 1. Now, right here, a lot of times people get this one confused because it's really hard to distinguish. This plus right here is a superscript, or an exponent. That's saying this is Ag plus 1. Over here, it looks almost identical. This is just a plus sign between the Ag and the iron. So that might have confused you because it is really, they look very similar. Yep, and because it stands alone. An element that stands alone has an oxidation number of 0. Okay, once we assign these, now it's easy to do our hookups. Our Fe, you can see increases in number, so that is our Leo Ra up right. Our Ag plus 1 goes down to Ag, so that decreases. That is our Ger OA down and left. Now you can write out your 2 half reactions. Oxidation is going to be Fe yielding Fe plus 3 electrons. Reduction is going to be, ignore the 3 for a moment, it'll be Ag plus 1 plus an electron yielding Ag. Okay, Mitch, at this point, our electrons lost and electron gains are not equal. We've got 3 here being lost, 1 here being gained, what do I need to do? I got 3 being lost, 1 electron being gained. What can I do to get those together? Yeah, I need to multiply everything on the right, the reduction half reaction, by 3. So go ahead and do that, and you get 3Ag plus 3 electrons yields 3Ag. And now we can do our addition. Caleb, when we add them up, what do we get for a coefficient on the Ag plus? So when we add these 2 half reactions together, this one on the left, this one on the right, what's our coefficient going to be on the Ag plus? Purposefully. So we're adding this half reaction underneath this one. What is the coefficient going to be on the Ag plus? Yep. So our Ag plus has a coefficient of 3. Right there it is. And so there's your answer. Good. Okay, let's have you check number 5 on your own. And what I would do is just have everyone write down, because it sounds like a lot of people might need to re-practice one of these. Write down your final answer right there. And then you can go back and re-hit that one if you need to. The final answer is 3Mg plus 2Cr plus 3 yields 3Mg plus 2 plus 2Cr. And then I want to do number 6.
Okay, if it goes up, it's the Leo, and the Leo is oxidation.
Okay, correct. If the oxidation number goes up, it's Leo, and loss of electrons is oxidation. If they ask for an agent, it is the reducing agent. Okay, but yes, you are exactly right in saying that. Everyone get number 5 written down? Correct answer? Just jot down your final answer right here, and I think you'll be able to get to it by using the process that we're describing above. And then we're going to do number 6 together, because there's a little bit of confusion there. So the actual answer, when you sum them, correct, is 10. Yep, no problem. And number 5 is identical to the ones we've done. Number 6 is a little bit different, so I want to hit that one in more detail. But number 5 is exactly like what we've done. Okay. Number 6. This one's a little bit different because it doesn't involve any atoms. It only involves ions. And so sometimes that throws people off because they have a hard time figuring out what is oxidized and what is reduced. The good news is you treat it the exact same way that we've done the others. So the first thing we're going to do is assign oxidation numbers, which is really easy because they're all equal to what, Cassie? Oxidation numbers for each of these is equal to the what's that? Close, but not the coefficient, the charge. Yep. So Fe is going to be plus 3. Go ahead, Cassie, finish it up.
2.
Yep.
2.
Yep. And 4. Okay. Going to Jess. Jess, give me some hookups here. What do we hook up our Fe plus 3 to? And we notice our number drops. So that represents Gur, OA, down, left. We'll notice that our tin, Sn plus 2 ion, goes up to plus 4. That becomes my Leo, Ra, up, and to the right. Now we're ready to write some half reactions. So we'll do our oxidation again on the left. We'll do our reduction on the right. We're going to Sophia. Sophia, give us our oxidation half reaction, if you would.
Sn plus 2.
Mm-hmm.
Yields Sn plus 4.
Mm-hmm. I agree it is the +2, and the reason why is you had to lose 2 from Sn +2 to get to +4. You lost 2 electrons, and it just moved you up by 2. So that goes there. Kaylee, can you do our reduction?
Fe plus 3
Mm-hmm.
plus 1 electron
Mm-hmm.
yields Fe plus 3.
Great job. Zoe, what do we do from here?
You're gonna multiply the Fe side by 2.
Very good. We need to multiply the Fe side by 2. What's the reason for that? Yeah, we need a match of electrons lost and gained. So we get 2 Fe plus 3 plus 2 electrons yields Fe plus 2. Krista, from this point on, what can I now do to both of those half reactions? I've got my electrons lost and my electrons gained, so I simply have to do what to get the overall? Very good. Add them together. So I'm going to bring my oxidation one down here underneath, just so I can add it easier. So this becomes my Sn plus 2 yields Sn plus 4 plus my 2 electrons. When I add them, Claudia, what cancels? Electrons can cancel out, and I get my overall reaction, 2Fe plus 3 plus Sn plus 2 yields Sn plus 4 plus Fe plus 2.
Is it 2 Fe or just Fe? Pretty sure it's 2 Fe.
You are absolutely correct. I did not carry, and that actually is one of the biggest mistakes that I just made. I did not distribute that 2 through to everything. That 2 has to get distributed to all 3 of those species, and if you don't do that, it'll
Okay, I have a
mess you up. Yes?
I thought the charges had to be equal.
Okay. On each side, they should be equal. Let's check them. 2 times plus 3 is plus 6. Then we've got another plus 2, so we have a total of plus 8. Make sense? On the left?
Oh,
On the right, we were going to have plus 4, so we do have plus 8. So the charge on the left balances the charge on the right.
I just added the other extra plus.
Okay. Yep, so you have to basically always multiply the coefficient by the charge to get the total charge. Good job. Okay. So tomorrow, I'll give you a quiz on writing half reactions using Table J.
Face. I feel like we go through this every time. I don't know. I think we can.
Well, again, you have to do it that way to get all points if you mess it up at the end. As long as you get it right.
Because I know the whole one was right, except for real.
Yeah, so if you get 100, I don't care how you do it, but I can't give you the partial credit necessarily unless I'm seeing the half reactions written out.
Well, I wrote them out. I just wrote like the 2 equations out and said how many electrons do I need. And then
It depends. If they specifically on the Regents exam faith say write the half reactions, they have to be done this way. If it simply says something like, when the equation is correctly balanced, what will the coefficients be? How you get that is up to you. But if they ask for the half reactions, you have to do it that way. So it depends a little bit on the type of question. You must be finding another way to cheat the system.
no, I don't do it with the thing.
You can do that in your head.
Yeah, I guess. I go from if you're losing electrons, then it's not going to be as negative or as low.
Okay,
Tractor's wheel, you got 5 minutes left.
that makes sense.
6 minutes left.
Okay. Please tell me the last time you've used a battery. When is the last time, how long ago has it been since you've actually used a battery?
In my TV remote.
This morning? Actually,
Caleb says this morning, and then he's changed it to right now. I'm gonna make a little wager here that you have not gone more than 15 minutes typically throughout the day with using some battery. Because every time you look at your phone, you are using, unless it's plugged in to the wall, you're using an internal battery. And that internal battery is made up of what? What type of battery is it called? Lithium and then something else. Lithium ion. Cassie got it. And if you read the back of your cell phone battery, it'll say a lithium ion battery, and it'll say this, 3.7 volts.
3.7.
Now, you guys are familiar with batteries because we use them all the time. You might be familiar with this guy, which is a AAA battery. You can see it there, AAA. And you may not know, however, the voltage it produces, but right here, you probably can't quite see it, it says 1.5 volts. Most things that use these batteries use how many of them? Could be from anywhere from 2 to 4. All right? Now what that means is, in physics we learn about hooking up batteries in series, and when you do that you add the voltage. So most things that run off of 2 AAAs are running off of 1.5 plus 1.5 volts, giving you a total of 3 volts. Okay? This guy here is a little different. Anyone buy one lately?
Oh yeah.
How much do they cost, roughly? Not that much. Yeah,
I bought 2
$7 or
the other
$8
day.
for a pack of 2. They're not cheap. And the reason why, you'll notice the voltage is 9 volts. Now, if you take 2 of these and stick them together, you've got 18 volts. What's your voltage of your car battery? Less than 18? No? 12 volts. Your car battery runs off of 12 volts. You can actually take 2 of these together and produce 18 volts. Now, obviously the size is different, so the car battery can provide 12 volts for a longer or an extended period of time, where this would deplete its voltage very quickly in terms of compared to a car battery. But the point is that's producing quite a few volts, all right? And that's why they're very expensive. So our lives, although we don't think of it, are dominated by the use of battery power. Most of us are using batteries every day, and many of you are using batteries within, I would say, every 5 to 10 minutes if you're looking at your phone. Maybe you shouldn't be.
My phone just like sits there and loses battery. Like if I like fully charge it and I don't touch it all day, it goes from like 100 to like 95. Even if I don't like touch it. Yeah.
And I know if it's searching for service, it can deplete it very quickly. What did it say?
Like so many things like make them go down. Like if you keep it plugged in longer than
Yeah.
100%,
Yes.
it ruins your battery. And if you plug it in when it's halfway between your
Yeah, they say
battery
when you get a new
percentage,
phone.
then
So
you
always
need
wait for it to
let
go
die
down
out.
and
Yeah.
then charge.
They said to like let it go to like 5% and don't be on it when it's plugged in.
They say when you first get your phone, like let it die first, like down first.
Really?
Yeah.
Okay, so what we're going to look at next, and this is really why this chapter is so important, is I know you don't think about it every time you use your phone that, hey, chemistry is taking place, but all of those batteries are driven by chemical reactions, okay? And they're driven by chemical redox reactions. So everything we're learning right now, one of the uses for it is in the use of batteries. So a couple of definitions here. We obviously have very little time, but basically an electrochemical cell involves a chemical reaction and a flow of electrons. So an electrochemical cell involves a chemical reaction that produces a flow of electrons. And we have really, we're going to kind of discuss two types of electrochemical cells. The first one is called a voltaic cell. And a voltaic cell uses spontaneous chemical reactions to produce the flow of electricity. Instead of saying produce here for this definition, I'm just going to say and involves. That's a little bit more accurate based upon it may not always produce, it could use just the flow of electricity.
This is what I did. I did a lot of it in my head just
Mhm.
it, I don't know. It clicks. Like I wrote all of
You're writing the
that's really-
half reactions down. Yeah, and then just show how you add them to get the total.
Okay.
Yep, I think you're basically doing everything, just internalizing it, except just write that full one down. I think you're good.
It's a thought process, not something
Yep.
to write out.
I'm okay with that.